Hello, friends. Welcome again in this new lecture on demystifying the method section, the computational cookbook. This is actually the part of that scientific writing of computational material science research. And now, in the previous lecture, I just emphasize the writing of that introduction section, the important part of that introduction section, and how we can refine each and every part of each and every paragraphs of that introduction section. Now, the next component, next part in IM RAD framework, that is M stands for method. So, in the methodology section, what are that important parts and how we will deal with during writing that research article. This is that the content for this lecture. So this is a comprehensive guide for graduate student and definitely early career researchers on writing precise reproducible method section in the DFT based research papers. I'm Dr. Manil Verma, your instructor of this course. Now, let's begin with the first question, why the method section matters. So this method section actually ensures reproducibility. The this one, and this provide the complete recipe that allows other researcher to replicate your computational experiments and verifying your findings. So this is that one of the importance of this method. And the second, this builds credibility. So this demonstrates methodological rigor and expertise, stabilizing your work at trustworthy within the scientific community. And this allows peer validation. So it enables reviewers and readers to thoroughly evaluate your computational approach and assess the validity of your conclusion. And this distinguishes rigorous research. So this separates through scientific work from superficial studies by documenting precise methodological data. So without clear method, computational result cannot be trusted or reproduced, uh, undermining the foundations of scientific progress. So that's these are that four sections for important matters parts by which we can say that method parts is uh, so important. Why? Now, some key principles of good method section. So, like a precise cookbook recipe, your method section must provide all the ingredients, steps needed for others to recreate your computational dish. A well crafted method section is. So, this is actually some sort of that important part of our recipe book, and by which you will prepare your beautiful tasty dish. So this well crafted method section, this is actually the complete one. So all parameters, settings and software details must be thoroughly reported. First, it must be complete. Second, that the it must be transparent also. So the methodology choice should be clearly justified with scientific reasoning. And then the reproducible, other researcher must be able to replicate your calculations precisely. I'm just this is that repetition whatever I previously mentioned in second lecture also, but this is important, and you should take care of each and every components of that method section. So it must be concise. So this avoid unnecessary details while including all essential informations. Then some software citations and some code citations. So the proper software citations is the foundation of computational reproducibility. Your method section must explicitly specify code number, important. So specify the exact software package used for your calculation. For example, if you are just mentioning wasp, I just prefer that you should also mention the full form of this wasp, that is Vienna AB Initio simulation package. For example, SISTA Spanish initiative for the electronic simulation with thousands of atom, quantum expresso, open source package for researcher in electronic structure simulation and optimization, Abinit, cache tape, CP2, etc. So I also just recommend that one should write the full form of that package. Although the familiar terms using in the scientific communities was Vasista, quantum expresso, Abinit, cache tape, CP2, etc. But the full form should be included with that. Now, the second part, that the version of that tool, so include the precise version used as implementation can change specifically between release, because uh, the capability as well as that whatever that particular tool can be performed in a specific version, it is mentioned there. Uh, if you are using older version and if you are presenting in your paper some advanced output, then it can be observed that it is not possible in the older version of that particular tool. So for example, this major revision that was for 5, was for 6, etc. In that minor revisions are there with the SISTA 5.4.1. It's presently we are using this, and then release date if relevant, uh, and the first release date with that the first stable reference of that one. And then this key reference cite the primary paper describing the software itself, major algorithm represent, and specific method implied. So this must be uh, given in form of reference for that methodology section. For example, the calculations were performed using SISTA tool with version is here, and that Solar et al. 2002. This is that reference for the site. Although here I am missing that full form of that, but one should write that full form of the SISTA package. Now, second term is that thing that is in computational material research, that is choosing and justifying the functional group. So exchange correlation functional, this is actually the heart of your DFT calculation, and the different functionals were different approximations and trade-offs. Generally, we begin with this LDA, local density approximation, and the reason behind this is a simplest approximation, and this tends to overbind the shorter bonds, and this higher energy, and this works well for metals, less so for molecules. So if you are working with metal, then if you are using that LDA, then you can mention, you can justify the use of that exchange correlation functionality. Second one is that ZZA. This is generalized gradient approximation, and that the PB, this is most widely used to balance accuracy. And if we are using that PB sol, then optimized for solid and surfaces. If you are using solids and surfaces, then one should use PB sol, and better for molecular geometry compared to that LDA. So this is that justification to use this GG. And there is some meta GGS also being used. So this scan and TPSS, this improved accuracy, better for surface and interfaces. Also this that solids and interface PB sol. And but remember, this is containing higher computational cost with compared to that ZZA. So if you have good computational power, and you want some more accurate result, then you should use this meta GG also. And then this hybrid functional. So this is not so far implemented in effective way. Although in a different version it is mentioned that some hybrid functions are being introduced, but still I am not able to use this hybrid functional in SISTA. But for other tools, you can mention this HSE06 or B3LYP. So this actually include that exact action, and for band gap calculation, because that other exchange correlation functions, generally we mention that it underestimates the band gap. So this is good for better band gaps, and significantly higher computational cost is there. So definitely we accuracy and computational power, if you want to good more accurate result, then computational power will be always more. So always justify your choice. Remember this, why you are choosing one particular exchange correlation function. For example, we use PBE, GGA PBE. Uh, it is balanced accuracy and computational cost for the transition metal oxides and has been well validated for similar system. And this is here you have to give the reference of that is GGA or concern that justification in some other papers also. Now, functional writing. So, example, the art of precise description, that is the especially that for that exchange correlation function. So, this this exchange correlation functional energy was described using the generalized gradient approximation with the Purdue-Berke-Irnhof PBE functional, which is well suited for layered oxide material. The choice was validated by comparing calculated lattice parameter with experimental values, showing agreement within 2%. This is that the proper justification of using up this exchange correlation function. So you can write, you have used that GG also. Yeah, you compare the result with the GG or other correlation functional, and you find that this GG is better. How much percent of better? You can also mention. For example, here it is mentioned that the lattice parameter is good agreement with experimental values within this window of 2%. And when let's notice for this example that exact functional type is ZZA, and the specific implementation that is PBE. This is that the name of that developer also, and also that the name of full author we have mentioned, and then justifies the material relevance. It is relevant to that material, and suitability for the system, and also validation approach, and qualifies this agreement with the experiments, and the expected accuracy that is 2%, and implement implicit validation effort. So these are that the proper way to write the use exchange correlation function. So this writing style balance technical precision with the clarity, providing sufficient detail while remaining concise. Now next is that is the use of that pseudo potential and PAW potential. So pseudo potential dramatically affect the calculation accuracy and efficiency, and your method must specify the pseudo potential type, which type of pseudo potential we are using. For example, that non-conserving, that accurate but computationally expensive non-conserving type pseudo potential. Ultra soft, this more efficient, slightly less transferable. These are that efficiency as well deficiency of that specific pseudo potential. And this projected argument wave PAW, efficiency is very high, and high efficiency, the accuracy, and it is widely used. So PAW and the source. So this is the one can use this pseudo potential from standard library like PS library, GPRW, JH code specific for WASP, PAW library, and there is sister repository is there that does like that, and custom generated specify generation parameter. And in case of that sister, we use this norm conserving Trollier Martin pseudo potential TM pseudo potential that is used in that system of 4.1.5, and nowadays we are using that PSML format of pseudo potential also, and one good database of this pseudo potential is available. And the valence configuration, even that we should mention that the pseudo potential with that valence configuration. For example, for potassium this is that the valence configuration, for oxygen this is valence configuration. So we are using this pseudo potential in this valence. And then the version inconsistency, so that version data of that pseudo potential library one should mention, and this consistent treatment across of all elements, so this must be mentioned in the valence electron configuration for each element. For example, here this example this we have mentioned. So this is that method one, the type of that pseudo potential. Second, the source of that pseudo potential from that specific uh, mm, website or a specific database we are using, and as well as uh, the version of that pseudo potential, and the configuration, that valence configuration of that each and every elements we must mention in the pseudopotential part. Next, in the methodology part, that is basis set and cutoff. So basis set determine the mathematical representation of electronic wave function, and their quality directly impact calculation accuracy and computational cost. So that in the plane wave codes like WASP, quantum X ratio, beneath, uh, that the energy cutoff reports in electron volt in WASP, Ry in quantum X ratio, and that example, a plane wave cutoff is 500 electron volt was used, and this is that method to writing for plane wave codes. And then charge density cutoff can be written in this plane wave based code if it is different from that wave function cutoff. And for example, the charge density cutoff was say to 4 times the wave function cutoff, means if you are taking this is 500, the four times we will mention here. And some localized basis codes like our SISTA and that PHI EMS. So the basis set quality, this is report size just like SZ, DZ, TZ, and DZP. So SZ is single zeta, this is single zeta, and then the double zeta polarization, and triple zeta polarization like D. So here that example, a double zeta plus polarization DZP basis set was implied. An energy set, so parameter controlling orbital extent and energy set of 50 milli electron volt was used for orbital confinement. So this is the main of method of writing these basis set and cutoff values. So always justify the choice. So the cutoff was chosen based on convergence set test showing orbital energy variation. It is less than 5 milli electron volt per atoms beyond this value. And then this key point sampling, this is important when we talk about some periodic crystals, periodic systems. So this key point sampling, this key point sampling determines how thoroughly you explore the brilliant zone, directly affecting electronic structure accuracy. So that periodicity, brilliant zone, symmetry points, this type of terms generally we use in solids. So for periodic materials, we use this key point sampling. So here we the grid density of type that is a 6 cross 6 cross 6 Monk pack key point grid was used. So this is that optimized Monk pack key point grid, and that is 6 cross 6 cross 6 because this is a three-dimensional bulk type things. And if you use a planar type structure, a monolayer, then we can use that is 6 cross 6 cross 1, and that it is along z axis, the vacuum is there. So 6 cross 6 cross 1, and for one single line one can write along z axis if it is periodic. So that is 1 cross 1 cross 6. So along a specific periodic direction we use this Monkhorst pack K points. Some special point, this including that zeta point. Zeta point is found as that stable point, and if relevant, we can use the zeta point. So density per reciprocal atoms, this corresponding to 500 K points per volume. So symmetry reduction, after symmetry operations, 47 irreducible K points remained. Convergence criteria, so convergence was achieved 8 cross 8 cross 8 K points with less than 10 milli electron volt change in the total energy. So this is that the writing methodology, writing techniques. For generally for optimization process, optimization purpose, we use that lower values of this K point 666, 888, 555 like that. But for electronic structure calculation, for band structure or dust calculation, generally we prefer some higher values of K points. So this higher symmetry, so high symmetry path definition, that easy zeta to x, m, and zeta, this is used for band structure calculation, dust calculation. number of k points along each segment we use, and a dense k mesh. For example, if you are using a 6 sixes, then we can use 18 cross 18 cross 18 three times in all direction. That is dense k points for DAS calculation as well as bend calculation. For 2D materials, you specify that this is for 2D materials. I have given that example there. So for bend calculation, we can take 12 cross 12 cross 1 or 18 cross 18 cross 1, 24, 24, 24, depending on your computational availability, computational power availability. And that vacuum separation along z direction, that is 20 electron volt, and whether the dipole corrections were applied. So common mistake, k point convergence is often underreported. It can dramatically affect calculated properties, especially for metals and small unit cells. So take care of that choosing this key point. This is not any random number. It's actually the converged point, and after a proper convergence test, we should use justified k points in a specific periodic direction. Some convergence criteria we mentioned in our methodology part. Although that methodology part is uh, maximum half page and more than half page, but each and every components of that methodology part is very important, so that the convergence criteria we mentioned, uh, the first one is that is 10 to the power 6 electron volt, that is electronic convergence. And this threshold for energy difference between electronic iteration, that determines when self consistency is achieved. And then 0.01 electron volt per angstrom, this is force threshold. It is written maximum allowed force on any atom for considering a structure as relaxed. And also one can write that stress and pressure criteria, that is 0.02 GPa. This tolerance for residual stress in variable cell optimization. So when we take this variable cell optimization, then we use this. Generally, I don't prefer this variable cell optimization. I don't want to keep that material as free. And then this charge density criteria. So convergence criteria for self-consistent charge density, this is 10 for minus 5 electron volt per volume. So these threshold defines the reliability of your calculation and must be explicitly stated. And the tighter convergence criteria generally yield more accurate result, but definitely this will uh, take some more computational power. And for example, in one sentence, we can write this as the electronic self-consistency loop was converged to 10 to the power 6 electron volt, while atomic positions were relaxed until the maximum force on any atom was below 0.01 electron volt per angstrom. For variable cell calculation, an additional criteria for that residual stress below 0.02 GP was applied. So when reporting unusual on system-specific convergence issue, briefly describe the approach used to overcome them. Now the convergence testing. So the convergence testing is essential to ensure reliable results while optimizing computational resources. For computational material science publication, systematic convergence testing should include step-by-step approach. Generally, in my paper, I mentioned that it is that the system is properly tested, or it is properly optimized by using 3 to 4 steps of that converging testing. So we start with that's that this cutoff values, k point densities, and basis side optimization. Even uh, generally we optimize that basis size, and then even exchange correlation function, exchange correlation functional, and then we move to mesh cutoff, in real space, and then this k point sampling in reciprocal space, and then final that lattice optimization. So energy monitoring, so plot total energy versus parameter value. Property convergence track change in key properties, for example that lattice constant, band gaps, etc. In this optimal selection, choose values when results plateau where minimum computational overhead. So include at least one convergent test figure. So we will get a different curve for different convergent test to include at least one. Specifically in my papers, we include that lattice variation with that different band, so that optimum lattice value. So supplementary information to demonstrate methodological rigor. So best practice report the specific convergence threshold used, not just the final parameter. For example, parameters were considered converged when the total energy changed by less than 1 milli electron volt per atom with further refinement. So now as a whole, let us give one good example of this method text. So calculation all calculations were performed with SISTA, version is V 4.1, and that reference is given. This is the first part. The exchange correlation energy was approximately using the generalized gradient approximation GGA with the PBE functional, and this writer Padu et al. Its reference is also mentioned, and this norm conserving Trulier-Martin pseudopotential I have mentioned were used with the double zeta plus polarization DZP basis set. A mesh cutoff, this is the converged name, mesh cutoff 250, and Monkhard's pack K points that grid is 8 cross 8 cross 8 were employed and converged to less than 5 milli electron volt per atom. Structure were released until force on all atoms below 0.01 electron volt per angstrom. So the complete here, the specific software is there, specific software there. This version functional is mentioned, pseudo potential is mentioned, basis cutoff is mentioned in convergence criteria, and reference include proper citation for software and method we have mentioned. Reproducible, okay. So contains all parameters needed to replicate the calculation. Efficiency present necessary information without excess text. So this method description provide all essential detail a peer would need to reproduce the computational approach while remaining readers uh, and focused. One bad example also, let me include. So we use DFT in SISTA calculation, calculate the structure complete. In one sentence, we have uh, just concluded the complete method section. We are using the DFT, and in DFT that is implemented in SISTA for the calculation. No, it's incomplete because here the functional is missing, pseudo potential is missing, basis set cutoff, and the other convergence criteria are missing. Even that unreferenced, no citation for reference and methods are given. It is not reproducible because the lacks of critical parameters needed to replicate the work, and this is too vague. So this generic description provide essential, not useful for methodological information. Consequences: this method description would almost certainly lead to rejection during peer review, or at minimum major revision request. It undermines the credibility of the entire paper by failing to demonstrate methodological rigor. So vague method sections like this are a red flag to reviewers and readers, suggesting either methodological uh, carelessness or deliberate abscration of details. Some typical language I'm using here. Now the next part, that is the figures and tables in method. So usually visual elements can generally enhance method clearly and digestibility. Consider include even we can include some computational workflow and form of that flow chart. So that flow chart is showing this flow chart showing the sequence of calculations and the decision points in your methodology. Parameter summary. So even we can give a table uh, to table of that different computational parameter. Concise table listing all computational parameters, especially helpful for complex workflow and multiple calculation type. And that the convergence plot, so graph showing energy or property convergence versus cutoff energy, k point density, and other key parameters, the convergent test. And then this model visualization, structure representation of supercell, especially interfaces or defects configuration to clearly system setup. So you are creating or removing one atom and creating that defect, so you can give the figure of that here. So the for length limited manuscript, so that consider moving details method figures to supplementary information while keeping a concise parameter table in main text. So hands-on exercise part 1. So analyze the following method section and identify missing or inadequate details. So example 1. So we performed DFT calculation using WASP. PB functional was used with 400 electron volt cutoff. The structure was relaxed and then electric properties were calculated. This is one sentence. So here, what are let's watch this sentence of 3 lines. And what are missing? First, the version of WASP, it is not mentioned here. Second, key point sampling details are not there in this sentence. And then the pseudo potential, that is PAW specification, it is not mentioned in this structure. Convergence criteria, it is missing. Also the citation, that is of WASP and others functional, missing. And that relaxation constraint, if any, these are missing in this sentence. So second example B. So first principle calculations were carried out to determine the electronic structure. The band gap was found to be 2.1 electron volt in good agreement with experimental value. What is missing? First, the software identification, functional choice for the criteria for band gap. All computational parameters are missing. Type of calculation like standard DFT or DW, these methods are missing. First principle calculations might be different. And this comparison methodology with experiment, this is missing. Structural information, all these are missing. So working in a small group, identify all missing details from both example. The questions would be need to ask the authors to reproduce their calculation. So you can take one any research paper and go to that methodology section and try to detect the missing parameter there, because if you want your paper must be uh, easily accepted by reviewers, editors, then you must take care of that methodology part also. For that, uh, you need the practice of all these things. So go through some papers and try to get this missing parameters and make a habit to write the complete specification of that method. Part 2, hands-on session. So take the uh, WAG method section below and rewrite it into the properly detailed reproducible form. So DFT was used to reduce the absorption of CO2 on the metal oxide surface. We found favorite absorption energy by WAG method. So rewriting process. In the rewriting process, identify missing components using the method checklist. Add specific details for each required parameter and include appropriate citation for methods and software. Clearly define calculated properties, yes, absorption energy formula, etc. Because here this carbon dioxide is absorbed on metal oxide surface, so that absorption energy formula must be mentioned in that methodology part. Share your rewritten version with your in the WhatsApp group for feedback. So this is that one hands-on exercise. So after completing your rewrite, we shall discuss at the discussion section and compare different approach. Focus on balancing completeness with conciseness while ensuring all critical information is included. Some common mistakes, just repeating all these things. This is some sort of that summary of whatever we have discussed. So common mistakes performed by different authors are no software version specified, omitting citation of original papers, not mentioning compilation options with relevance, and functional choice issues, that is no justification for functional section, using inappropriate functional for the property. We know that this function is not suitable for that specific property and we are using that, and not acknowledging uh, about that limitations of that functional. Parameter ambiguity, so missing convergence thresholds, unclear k-point sampling scheme, vague pseudo potential description, and that this calculation details omission, so not specified supercell dimension, and that omitting a treatment of magnetism and following the describing a correction scheme. Just for example, that we are using Humbert correction there, GGA plus U, DFT plus U, and we are missing that this correction scheme there. So these errors undetermined reproducibility and the scientific credibility. Even excellent researcher can be rejected due to poor method reporting. So when describing complex or multi-stage calculation, consider organizing method by calculation time rather than typing to the presence of parameters in single paragraph. So best practice, just a reminder what you have to do. So cite foundation paper, always cite the original DFT method papers, core algorithm, and specific implementation used in your work. Create parameter table, provide a concise summary table of all computational parameters, especially helpful for manuscript with space limitations, and this will help to reviewer to understand your paper easily. And report all threshold explicitly state all convergence criteria and tolerance applied in calculation. Use supplementary information if there. So if general space is limited, move detailed parameter discussion and convergent test on the supplementary information form while maintaining core parameters in the main text. So that document specific approach, so clearly describe any non-standard technique, corrections, or custom implementation used in your calculation. So one methods section is not just our documentation, it is our scientific contact with the reader and establish trust and enable scientific progress. So these practices significantly improve paper quality, enhance reproducibility, and increase the likelihood of successful peer review. They also build your reputation as a thorough, trustworthy researchers in the computational material science community. So this methodology part is important part. As I so some assignment we can I can suggest that select that recent paper, find one computational material science paper published in last 2 3 years, and read that paper, specifically that methodology part. Analyze the method sections, what is given extra or which is not mentioned in this lecture, and that missing part of that paper. So evaluate that method section for completeness, clarity, and reproducibility using the section. Then identify the gap. List any missing parameter, unclear descriptor, or inadequate justification that would have reproducibility. And also suggest improvements. So rewrite one paragraph of the method section to improve its clarity and reproducibility. So this is for the practice. You can read some papers and go through its method section, and this will polish your work. And when you will start writing on your methodology part, all these things will be uh, uh, this thing will help you to refine your methodology section. These are that the different references I have included in this lecture. Anyway, so thank you all, and I think now you will be quite able to write your methodology section of your computational based research. Thank you all. Practice well, learn well, apply well. Meet you in the next section.